Hello! Please settle in, close your eyes, and prepare for a journey. Today we won't be traveling to distant stars or exotic planets. Our path leads into the very core of reality, into its most fundamental and mysterious fabric, time itself. Have you ever experienced déjà vu, that strange, fleeting feeling that the moment you are living through has already happened before? Now imagine that same feeling stretched across the scale of the entire universe. What if not just a fleeting moment, but the whole history of the cosmos, from the first flash of light to the last dying atom, is merely a repetition? In this sleep lecture, we will explore one of the most dizzying ideas in science and philosophy, the hypothesis that time is not linear, that it does not fly like a straight arrow from past to future, but instead closes in on itself, forming a colossal, eternal loop. We'll discuss what might have existed before the Big Bang and what awaits us after the end of everything. I promise you that by the end of this journey, your perspective on the universe, and perhaps even on your own life, will never quite be the same. Let us now dive into the anomaly of time, where the cosmos flows in a circle. Before we plunge into the deep currents of cyclical theories, let's refresh our memory of the worldview that most of us consider canonical: the story of linear time. It begins approximately 13.8 billion years ago, at this moment, from a state of unimaginable density and temperature, what scientists call a singularity. Everything is born: all space, all matter, all energy, and time itself. This is the event we call the Big Bang. From that instant, the universe begins to expand and cool. The first particles appear, which then assemble into atoms. Gravity asserts its dominance, forming the first stars and galaxies out of gas clouds. Stars live and die, forging heavy elements within their cores, the elements that would later form planets and, eventually, you and me. This story is elegant, coherent, and backed by countless observations, from the cosmic microwave background radiation left over from those ancient times to the observable recession of distant galaxies. In this model, the universe has a clear beginning, but this is also where its major challenge lies, its Achilles heel. If time had a beginning, then what existed before it? The question itself seems nonsensical within the theory's framework, because if time didn't exist, the concept of before cannot apply. It's like trying to walk north from the North Pole. The physical laws as we know them simply break down at the point of singularity. It is a wall that our current science cannot peer beyond. And it is this unsatisfactory nothing or unknowable answer that has compelled scientists to search for alternatives. What if the Big Bang was not the absolute start of everything, but merely a transitional moment in a far grander, eternal narrative? Let us begin our shared journey into the depths of cosmos and consciousness with the most fundamental inquiry, one that has accompanied humanity throughout history like an eternal companion. What is time? Our intuitive, everyday understanding paints a simple, clear picture. Time is a river, an unrelenting, sweeping river that flows in only one direction. It begins in the misty source we call the past, carries its waters through the fleeting moment of the present, and rushes into the infinite ocean of the future. We are tiny vessels on this river, unable to turn back or halt the current. Every heartbeat, every breath, every change of day and night seems only to confirm this irrefutable truth. Our entire civilization, our personal lives, are built upon this linear axis. We mark birthdays, celebrate anniversaries, and plan for tomorrow, for next year, for decades ahead, always with the certainty that the past is behind us and the future is yet to arrive. This concept, the concept of the arrow of time, flying from point A to point B, is so deeply woven into the fabric of our thought and language that any alternative seems not merely strange, but almost heretical, violating the fundamental laws of existence. We say, time heals, time is up, or only time will tell, and all these phrases presuppose its irreversibility. But what if this familiar and convenient model is merely a local illusion, an illusion generated by our specific human scale of perception? much like the illusion of a flat Earth to a person standing in a field. What if, on the colossal, unimaginable scales of the entire universe, this river of time doesn't flow into an ocean of oblivion at all? What if, after making a gigantic universal sweep, it returns to its origin, closing itself into an eternal, incomprehensible loop? In this striking paradigm, our world has neither an absolute beginning nor a final end. There is no unique act of creation and no ultimate heat death. There is only an endless pulsating cycle of cosmic breath. An inhale, the birth of the universe. An exhale, its fading away. And then another inhale, another birth. The idea that the Big Bang, which modern science considers the starting point of all existence, all matter, energy, space, and time itself, might not have been a unique event, but merely one beat in a series of infinite repetitions. This idea is capable of rattling the very foundations of our worldview. This is not merely an abstract scientific hypothesis, it is a profound philosophical concept that forces us to ask, who are we in this eternal recurrence? Do our lives repeat? And is there any meaning left in the word first time? In this lecture, under the cloak of night, we will allow ourselves to depart from familiar shores and sail through the boldest and strangest currents of modern cosmology to explore this fascinating anomaly, the possibility that the cosmos flows in an endless loop. The concept of cosmic cycles is hardly new. In fact, it's as ancient as human thought itself. Ancient civilizations across the globe, from the Hindus, with their concepts of kalpas and yugas, to the Greeks with their great year, where all celestial bodies return to their starting positions, intuitively grasped this repetitive nature of existence. They observed the cycles of nature, the changing seasons, the water cycle, life and death, sleep and wakefulness. It was only natural for them to extrapolate these earthly rhythms onto the entire cosmos. The world, they believed, was born from chaos, lived through its golden, silver, bronze and iron ages, and then was destroyed, only to be reborn again. In these ancient myths and philosophical systems, there was no horror associated with the end of the world, because an end always implied a new beginning. It offered a comforting, harmonious worldview where nothing truly vanishes, it merely transforms. However, with the onset of the scientific revolution and the development of thermodynamics in the 19th century, this cyclical model hit a major roadblock. That roadblock was the concept of entropy. The second law of thermodynamics, one of the most fundamental laws of physics, states that in a closed system, total entropy, the measure of disorder, can only increase. The universe, as far as we can tell, functions precisely as such a closed system. Every event, every process within it, increases the overall chaos. Heat dissipates, order breaks down. A star radiates energy and eventually goes dark. A complex molecule disintegrates into simpler atoms. This irreversible increase in entropy is precisely what we perceive as the arrow of time. It is what distinguishes the past from the future. Even if the universe were to simply shrink back on itself, it would not return to its original, ordered state. Instead, it would contract into an incredibly hot, chaotic mess with extraordinarily high entropy. It's like breaking an egg and then trying to force it back together by simply reversing the video. The video might work, but reality never will. The second law of thermodynamics appeared to have delivered a death blow to all cyclical models. The universe could only be born once, live out its life by increasing disorder, and then die a final heat death where all energy is uniformly distributed in cold, empty space. But as we shall see, the boldest minds of the 20th and 21st centuries have found clever ways to overturn this sentence. The first and perhaps most intuitive modern model of a cyclic universe is called the Big Bounce theory. It is essentially a direct evolution and rethinking of the standard Big Bang model. Imagine throwing a ball onto the floor. It drops down, compresses on impact, and then bounces back up, expanding again as it flies. Now let's imagine that our entire universe is that giant ball. Right now, we are in the upward flight phase, post-bounce. The universe is expanding, galaxies are flying away from each other, space itself is stretching out. But according to this theory, this expansion won't last forever. At some point, many billions of years from now, gravity, the attractive force of all matter and energy in the universe, will overcome the initial explosion's momentum. The expansion will slow down, stop, and then reverse into contraction. This coming epoch is often called the Big Crunch, or sometimes the Big Collapse. The universe will begin to shrink, galaxies will rush toward one another, temperature and density will steadily increase, stars and planets will be torn apart, and eventually atoms will break down into elementary particles. Ultimately, all matter in the universe will collapse into a single point, much like the singularity from which everything began. And this is where the theory gets really interesting. Instead of just vanishing into oblivion, this ultra-dense point, thanks to the still poorly understood laws of quantum gravity, actually bounces. A new Big Bang occurs, initiating the next cycle, a brand new universe, possibly one with entirely different physical laws. This model elegantly solves the philosophical problem of what happened before the Big Bang. The answer is simple. There was the previous contracting universe. There is no true beginning, only an endless sequence of cycles of expansion and contraction, cosmic breaths in and out. It's like the eternal beating of a gigantic cosmic heart. However, this beautiful theory faces one major problem, and its name is dark energy. Observations from the late 20th century revealed that the expansion of our universe is not slowing down due to gravity. Quite the opposite. It's accelerating. Scientists believe this acceleration is caused by mysterious dark energy, an anti-gravitational force distributed throughout space. If its effect doesn't stop, there will be no big crunch. The universe faces eternal expansion and a cold death. But even here, proponents of the cyclic model still have their counter-arguments. So we now face the primary antagonist to the Big Crunch theory, the mysterious dark energy. This invisible substance, estimated to account for almost 70% of all the energy in the universe, effectively acts as anti-gravity. Instead of attracting, it repels, forcing space to expand faster and faster. If dark energy continues to behave this way indefinitely, gravity will never be able to halt the expansion and reverse it. Instead of a big crunch, we would face either the big rip or the big freeze. In the first scenario, the accelerating expansion would eventually become so powerful that it would tear apart galaxies first, then star systems, then planets, and ultimately the very atoms themselves. In the second, calmer but perhaps bleaker scenario, the universe expands forever. Stars burn out, matter decays, and the cosmos turns into an infinite, cold, dark, and lifeless wasteland. Both options imply an absolute and final end. But is dark energy truly that all-powerful? Proponents of the cyclic model suggest otherwise. They hypothesize about something called quintessence, or phantom energy. Unlike the cosmological constant, introduced by Einstein, which, as the name implies, is unchangeable, quintessence could shift its properties over time. Imagine dark energy not as a constant background force, but as a dynamic field. In our current epoch, this field exhibits repulsive properties, causing accelerated expansion. But what if, in tens or hundreds of billions of years, this field changes its sign? What if that repulsive force suddenly becomes attractive? In that scenario, dark energy would transform from the Big Crunch's enemy into its most powerful ally. It would begin assisting gravity in contracting the universe, doing so far more efficiently. This is the mechanism that could potentially trigger a big bounce even in a universe currently dominated by dark energy. Of course, these remain purely theoretical postulates. We still know far too little about the true nature of dark energy, but the mere possibility that this force is neither eternal nor constant leaves the door open for cyclic models. Perhaps the universe is playing the long game, and the current phase of accelerated expansion is just a temporary stage in the eternal cosmic dance of contraction and expansion. Even if we solve the dark energy problem, a second, even more formidable opponent to the idea of a cyclic universe remains: the the second law of thermodynamics and the relentless march of increasing entropy. Let's explore this concept a bit more closely, as it is key to understanding the arrow of time. Think about your own room. If you don't make an effort to clean it, over time, it will inevitably become messier. Things will end up out of place and dust will accumulate. Disorder or chaos will steadily increase. To restore order, you have to expend energy. The same principle applies to the universe. Any process converts ordered, useful energy into disordered, dissipated thermal energy. A star is a highly ordered system, concentrating vast amounts of energy. By radiating light and heat, it scatters this energy into the surrounding space, thereby increasing the overall entropy. Now let's imagine our universe completes a cycle, expansion followed by contraction. Every such cycle generates massive amounts of entropy. This means that each subsequent cycle must begin with a higher level of disorder than the one before it. It will be messier. The universe after a rebound will be larger and will last longer than the previous one. And this trend continues with every cycle. If we run this logic backward in time, we find that preceding cycles must have been shorter and smaller. Eventually, we are forced back to the very first, smallest and most ordered cycle. In other words, we run squarely into the problem of the beginning all over again. Cycles simply cannot be eternal if they become more entropic each time. It's like making a copy of a copy. With each reproduction, the image quality degrades until it eventually becomes unrecognizable. Likewise, with every cycle, the universe would become increasingly chaotic and diluted until the cycles eventually stop. This problem seemed utterly unsolvable. For the cycles to be truly eternal, we would need a mechanism that could reset the entropy at the end of each cycle, a complete cosmic spring cleaning, returning the universe to its initial low entropy state. And just such a mechanism has been proposed by one of the greatest physicists of our time. The solution to the problem of increasing entropy emerged from an unexpected source. It was proposed by Sir Roger Penrose, Nobel laureate, and arguably one of the most original thinkers in modern physics. His theory is known as conformal cyclic cosmology. That sounds complicated, but the core idea is strikingly elegant. Penrose asks us to look toward the very, very end of our universe, specifically if it is destined for eternal expansion rather than eventual collapse. Imagine a future an unimaginable number of years from now when all stars have burned out, all matter has decayed into elementary particles through proton decay, and even black holes have evaporated via Hawking radiation. What remains? Only a cold, dark, empty universe filled solely with photons, massless particles of light, and perhaps other massless particles like gravitons and neutrinos. In such a universe, one devoid of massive objects that could serve as clocks or rulers, the very concepts of time and distance lose their meaning. For a photon traveling at the speed of light, time doesn't flow and distance doesn't exist. It is simultaneously at the beginning and the end of its journey. In a universe stripped of mass, the laws of physics become conformally invariant. This means physics does not change when the scale changes. A universe stretched to gargantuan size becomes physically indistinguishable from a universe compressed to a microscopic point. And here lies Penrose's stroke of genius. He argues that this cold, empty, infinitely vast end of our universe, what he calls our aeon, is mathematically equivalent to the hot, dense, infinitely small beginning of the next universe, a brand new Big Bang. A conformal rescaling occurs. The infinitely distant future of one aeon seamlessly becomes the singularity point for the next. But what happens to entropy? According to Penrose, all the vast entropy of our aeon, primarily contained within the cosmic microwave background radiation, becomes the very fuel that ensures order and low entropy at the start of the next aeon. The gravitational field essentially absorbs all the chaos and is reborn into a smooth, uniform state, ready for a new cycle. Thus, the end is the beginning. The universe is eternally reborn, transitioning from a state of infinite emptiness to one of infinite density and cycling onward forever. Roger Penrose's theory isn't just a beautiful mathematical abstraction, it yields concrete, testable predictions. If our universe truly is just one eon in an infinite cycle, then residual traces of the previous eon should remain visible within it. Penrose suggested these traces might take the form of what he calls Hawking points. Let's break down what those are. In the previous eon, just as in ours, there were supermassive black holes. They acted as the gravitational centers of galaxies, consuming matter for trillions of years. According to Stephen Hawking's theory, black holes are not immortal. They slowly evaporate, emitting energy in the form of particles, what we know as Hawking radiation. Near the very end of their lives, once a black hole has shed almost all its mass, this process culminates in a powerful burst of energy. On the timescale of a single eon, these bursts happen in the unimaginably distant future. But from the perspective of the next eon, which emerges from the previous one's end, these energy flashes look like points imprinted right at the dawn of time. Penrose argues that all the energy emitted by a supermassive black hole throughout its evaporation will be concentrated in a single, minuscule point on the map of the cosmic microwave background, the residual echo of the Big Bang that we observe today. These points should appear as anomalously hot spots against the uniform microwave background. Their projected size should be several times the diameter of the Moon in our sky, and the most astonishing claim is that Penrose and his colleagues assert they have already found such points. Analyzing data gathered by cosmic telescopes, they detected several anomalous regions that align with the theory's predictions. Naturally, the scientific community treats these claims with considerable skepticism. Many believe these points could simply be random fluctuations or artifacts from data processing, yet the mere possibility that we could be looking at the ghosts of black holes from a previous universe is truly breathtaking. If the existence of Hawking points is confirmed by independent research, it would represent one of the greatest discoveries in the history of science and provide powerful evidence that our universe is merely a link in an eternal chain of cosmic rebirths. Setting aside Penrose's elegant, though currently controversial theory, there exists a completely different approach to the concept of a cyclic universe. This idea emerges from the most advanced and abstract fields of theoretical physics, namely string theory and M-theory. These theories attempt to unify all fundamental forces of nature into a single theory of everything. Within these models, our familiar four-dimensional universe, comprising 3 spatial dimensions and 1 of time, is far from the whole picture. It is merely a brane, a membrane floating within a multidimensional volume known as hyperspace or the bulk. Imagine 2 sheets of paper hanging parallel to each other in a vast room. Each sheet represents a separate brane universe. In this specific framework, dubbed ekpyrotic or brane cosmology, the Big Bang was not the genesis of existence. Instead, it was the explosive result of a collision between 2 such parallel brane universes. These branes slowly drift throughout hyperspace. Periodically, perhaps once every trillion years, they inevitably collide. This collision instantly releases the colossal burst of energy that we observe as the Big Bang. Following the impact, the branes bounce apart and begin separating. Our resulting universe expands and cools, allowing life to eventually take root. But once these branes reach their maximum separation distance, they are pulled back together by a mysterious force operating within the bulk. Trillions of years later, the cycle culminates in a new collision, a fresh Big Bang, that obliterates the old universe and instantaneously spawns a new one. This model also elegantly resolves several key problems plaguing standard cosmology. For instance, it explains the universe's remarkable homogeneity and flatness. This is because the branes, prior to impact, were extremely cold, nearly empty, and perfectly parallel. The resulting collision occurred simultaneously across their entire surface, generating a perfectly uniform flash of energy. Crucially, this model avoids the problem of the singularity entirely. While temperature and density at the moment of collision are enormous, they remain finite. The fundamental laws of physics never break down, and finally, it resolves the ultimate problem of the beginning. Our Big Bang was simply preceded by an earlier collision. It is an eternal cycle of impact and recession, creation and destruction. Our universe, therefore, is merely one act in this infinite cosmic drama playing out across unseen higher dimensions. Let's take a step back and return to the fundamental concept underpinning our perception of time: the arrow of time itself. Why is it that we remember the past but never the future? Why can a glass shatter, yet the shards can't spontaneously reassemble themselves? As we've discussed, physicists attribute this phenomenon to the relentless increase in entropy. The past is characterized by low entropy, order, while the future is defined by high entropy, chaos. But what if the thermodynamic arrow isn't the sole source of time's direction? There is another major contender, the cosmological arrow of time, which is directly linked to the expansion of the universe. We exist in an expanding universe. This expansion provides the necessary stability for the formation of galaxies, stars, and life itself. In a hypothetical contracting universe, everything would be vastly different. The night sky wouldn't be dark, it would be dazzlingly bright, as light from distant galaxies would be blue-shifted, not red-shifted, making it increasingly energetic. Such a universe would be too chaotic for complex structures like us to form. Therefore, the very fact of our existence as observers strongly suggests we must reside in an expanding phase. This is known as the anthropic principle, but what happens if, perhaps in a cyclical model of the cosmos, these two arrows, the thermodynamic and the cosmological, don't always align? Some scientists, notably Sean Carroll, propose a startling hypothesis: the two-arrow universe. Imagine a central pivot point, the Big Bang. From this single origin, time flows in two opposite directions. In one direction, the universe expands and entropy increases, that's our world. But in the other, mirrored direction, another universe exists. It too expands away from the same Big Bang, and its entropy also increases, but its future is what we perceive as the absolute past. It's like two distinct streams flowing away from a single source. In this model, the universe doesn't have a single future, but two. And rather than having a single past, it shares a common point of birth. This is an even stranger and more counterintuitive concept, but it fundamentally attempts to solve the puzzle of why our past started in such a remarkably low entropy state. Perhaps our universe is just one of two twins born from that single event, and somewhere out there, in the direction we perceive as the deep past, exists an anti-universe for which we are its past. This profound idea blurs the boundary between past and future at the most fundamental level, forcing us to consider that our linear perception of time might be far more limited than we ever imagined. As we delve into the hypotheses of a cyclic universe, one intriguing question immediately arises. Will the fundamental physical laws and constants remain the same in every new cycle? In the standard Big Bang model, we are, arguably, incredibly lucky. Fundamental constants like the speed of light, the gravitational constant, and the electron's charge possess precisely the values required for the existence of complex chemistry, stars, and ultimately life. If even one of these constants was slightly different, the universe would be entirely unrecognizable, perhaps starless, composed only of hydrogen, or collapsing back into a singularity a fraction of a second after its birth. This phenomenon is known as the fine-tuning of the universe. In the cyclic model, however, this question becomes even more fascinating. There are two primary scenarios. The first possibility suggests that every bounce or brane collision completely resets the physics. Each new cycle is born with a randomized set of fundamental constants. This situation leads to a form of cosmic natural selection. Countless universes are born and die, but only those where the constants are favorable survive long enough for complex life and intelligent observers to evolve. Our existence in such a successful universe isn't a miracle, but simply a statistical inevitability. We exist here and now precisely because the laws of this particular universe allow for it. In countless other cycles, there may be no one at all to ask this question. The second scenario, conversely, posits that the physical laws are immutable, passed down from cycle to cycle. Perhaps they are encoded within the very structure of the multidimensional bulk where the branes collide, or they are an inherent property of the bounce mechanism itself. In this case, our universe is not a cosmic accident. It is the inevitable outcome of an eternal process governed by the same unwavering rules. Every cycle would be fundamentally identical to the last. It would contain the same particles, the same forces, and the exact same constants. While this doesn't preclude differences in details, the arrangement of galaxies or the history of specific planets, the underlying basic structure would always be preserved. Currently, we have no way of knowing which of these scenarios is correct, but the mere act of asking this question pushes us to a new level of understanding our place in the cosmos. Are we the product of a random cosmic lottery, or the predictable result of an eternal, immutable law? Contemplating the cycles of the universe inevitably carries us beyond the realm of pure physics and straight into philosophy. It is here we encounter a concept that captivated thinkers long before the advent of string theory or conformal cosmology: the concept of eternal recurrence. The German philosopher Friedrich Nietzsche articulated it most vividly. Imagine a demon appearing to you in your deepest solitude and saying, "This life, which you are now living and have lived, you will have to live again, and innumerable times more, and there will be nothing new in it, but every pain and every joy, every thought and every sigh, and everything unutterably small or great in your life must return to you, all in the same sequence and succession." How would you react to those words? Would you fall to your knees, gnashing your teeth and cursing this demon? Or would you experience sheer exhilaration, understanding that your every action, every decision now carries the weight of eternity? For Nietzsche, this was purely a thought experiment, a litmus test for the strength of the human spirit. Could a person love their life so profoundly as to desire its endless repetition in the minutest detail? This concept, known as amor fati, or the love of fate, becomes the centerpiece. But what if this is more than just a philosophical exercise? What if the cyclical model of the universe holds true, and every cycle is an exact duplicate of the one before it? Quantum mechanics suggests that the world is probabilistic at its most fundamental level. However, if the universe is finite in its volume and content, the number of possible particle configurations, while unimaginably vast, remains finite. In an infinite sequence of cycles, any finite probability must eventually be realized. And not just realized once, but an infinite number of times. This implies that somewhere in the endless chain of universes, an exact copy of our solar system, our planet, and ultimately of you, will be born. You will live that exact same life, committing the same errors and claiming the same triumphs, and this will happen again and again and again. This thought can be equally terrifying and liberating. It strips our actions of any unique significance, yet simultaneously grants them infinite weight. Every choice you make, every act of kindness or malice, literally echoes in eternity, not just metaphorically but factually. Let's step back from the vast cosmic scale for a moment and focus on the concept of the cycle itself, the fundamental principle that organizes matter and information. Cycles are everywhere we look, and that is no coincidence. Our planet spins on its axis, creating the cycle of day and night. It orbits the sun, generating the cycle of the seasons. These astronomical cycles underpin all biological rhythms on Earth. Bird migrations, animal hibernation, the blooming of plants, they are all governed by this great cosmic clock. Water on our planet exists in a perpetual circulation: evaporation, condensation, precipitation, runoff, and then evaporation once more. Carbon, oxygen, nitrogen, all the key elements of life follow their own biogeochemical cycles, moving from the non-living environment into living organisms and back again. Life itself is a cycle of birth, growth, reproduction, and death, ensuring the continuity of the species. Even within our own bodies, we observe countless cycles: the rhythm of breath, the cycle of the heartbeat, the loop of sleeping and waking. Our cells are constantly being renewed within their own life cycles. Perhaps the universe as a whole is organized on this very principle because cyclicity is the most efficient and sustainable method for complex systems to exist. A linear system, one with a defined beginning and end, is inherently wasteful. It consumes resources and moves toward inevitable depletion. A cyclical system, however, is capable of self-renewal and maintaining stability over vast stretches of time. It recycles its own output, turning the end of one process into the start of the next. Could it be that entropy, which we regard as an absolute law leading to decay, is, at the most fundamental level, integrated into a global cycle we are not yet able to perceive? Perhaps the increase in disorder in one part of the system is compensated by an increase in order somewhere else. Or perhaps, as suggested by Penrose's theory, maximum disorder itself becomes the transition point to a new order. If this is the case, then our universe doesn't just exist, it lives, it breathes, it pulses, it renews itself. And we, with all our tiny earthly cycles, are merely a fractal reflection of this great universal process. One of the most compelling arguments for the standard Big Bang model is the so-called relic radiation, or, as we know it, the cosmic microwave background, CMB. This faint electromagnetic radiation, which uniformly fills the entire universe, is essentially the echo of the Big Bang. For the first 380,000 years after its birth, the universe was so hot and dense that it was essentially an opaque fog of plasma. Light couldn't travel freely, constantly scattering off free electrons. But once the universe expanded and cooled sufficiently, protons and electrons were finally able to combine, forming neutral hydrogen atoms. The universe became transparent to light, and the very light that was released at that moment is still traveling through space today, having cooled due to expansion to a temperature of just 2.7 degrees above absolute zero. The map of this relic radiation is, in essence, a photograph of the infant universe. It carries an enormous amount of information about the universe's birth and early evolution. But how do cyclic models account for the existence of this background? In the Big Bounce model, the explanation is fairly straightforward. Each new Big Bang, or bounce, generates its own hot plasma phase and subsequently its own CMB. The radiation we observe today is simply the echo of the most recent bounce. The relic radiation from previous cycles was completely destroyed and remelted by the extreme conditions of the preceding Big Crunch. The situation in Penrose's model is somewhat different and more intriguing. The CMB of our current eon is essentially a transformed and rescaled background originating from the far future of the previous eon. All the energy scattered throughout the cosmos at the end of our cycle becomes high-energy radiation at the start of the next. Furthermore, the Hawking points we have discussed are believed to be direct imprints of black hole activity from the previous eon visible in the CMB of our own. In the colliding brane model, the relic radiation is likewise born at the moment of impact. The energy of the collision heats the branes to super-high temperatures, creating the hot plasma that subsequently cools and becomes transparent. Thus, all major cyclic models are capable of explaining the existence of the CMB. Moreover, they predict certain subtle features within it that may differ from the predictions of the standard inflationary model, and the search for these minute differences in the data gathered by modern telescopes is currently one of the most active battlegrounds between proponents of linear and cyclic cosmology. Whenever we discuss the universe's birth, whether it was a unique Big Bang event or one of the predicted cyclic bounces, we immediately run into the puzzle of the early cosmos's striking uniformity. If we look at the map of the cosmic microwave background radiation, or CMB, we see that temperatures across different parts of the sky vary by only 1 part in 100,000. This tells us the early universe was astonishingly uniform in all directions. In the standard Big Bang model, this presents a significant challenge known as the horizon problem. Different regions of the universe that we observe on opposite sides of the sky were, in the earliest moments, too far apart for light to have traveled between them. They couldn't have communicated or coordinated to equalize their temperatures. This challenge is typically solved by the theory of inflation, the hypothesis that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponentially fast superluminal expansion. It ballooned from a subatomic size to the size of a grapefruit in a vanishingly small amount of time. This rapid expansion effectively smoothed out all the initial irregularities, resulting in the highly uniform universe we see today. But how do cyclic models address this same issue? The Big Bounce model offers its own solution. Before the current contraction phase began, the previous iteration of the universe existed for a vast period. This gave all its constituent parts enough time to reach thermal equilibrium. The subsequent slow contraction phase then preserves this uniformity. Thus, the universe arrives at the moment of the bounce already smooth and uniform, meaning it doesn't require an extra inflationary stage immediately after its birth. In the colliding brane model, or ekpyrotic model, homogeneity is also explained naturally. The branes slowly approach each other over trillions of years before the collision. They are cold, nearly empty, and extremely smooth. The collision occurs simultaneously across their entire surface, generating a uniform burst of energy. Therefore, cyclic models not only offer an alternative to the initial singularity, but also explain key observable properties of our universe, doing so, according to their proponents, more naturally, and without introducing extra entities like the hypothetical inflation field. They replace one mystery, what preceded the Big Bang and why it was so specific, with another, perhaps more fundamental puzzle, that of an eternal, self-sustaining cycle. It represents a paradigm shift, moving away from a unique creation event towards a ceaseless process of cosmic rebirth. Let's revisit the concept of eternal recurrence, but approach it this time through the lens of information science. A foundational principle of physics states that information cannot be destroyed. This principle is at the heart of the infamous black hole information paradox. When an object falls into a black hole, all the information about it, its composition, structure, and history, seems to vanish forever. This directly violates the laws of quantum mechanics. Stephen Hawking and other physicists struggled with this problem for decades. Today, the consensus leans toward the idea that the information is somehow preserved, perhaps encoded, on the surface of the event horizon or within Hawking radiation itself. Now let's apply this principle to a cyclic universe. If information cannot be destroyed, what happens to it during a big crunch or a brane collision? Is the information from the preceding cycle retained? If so, in what form? It suggests that perhaps each new cycle doesn't start with a completely blank slate. Maybe the memory of previous iterations is somehow encoded within it. This retention might manifest as subtle fluctuations in the cosmic microwave background or in the large-scale distribution of galaxies. Think of it like a book that is erased and rewritten, but faint traces of the old letters remain on the pages. Some bold hypotheses take this idea even further. For instance, physicist Lee Smolin suggests in his theory of cosmological natural selection that universes reproduce by forming black holes. Every black hole within our universe gives birth to a new universe with slightly altered physical laws. The universes that survive, meaning the ones that produce the most black holes, are those whose laws are most favorable to that production. In this model, information from the parent universe is passed on to the child universe, but with small mutations. This leads to the evolution of universes, making them increasingly better adapted for existence. In this worldview, eternal recurrence isn't a precise repetition of the same events, but rather an eternal evolution, a constant cosmic self-improvement. Every cycle isn't identical to the last. Instead, it is a descendant, carrying its legacy while introducing novel elements. This transforms the universe from a static, repeating machine into a living, developing organism that learns from its past lives. The thought that we exist within a universe that is the product of trillions of years of such cosmic evolution is arguably even more compelling than the simple idea of repetition. All the cyclic models we discuss eventually hit the same wall as standard cosmology: the need to unify the two pillars of modern physics, Einstein's general relativity and quantum mechanics. Relativity excels at describing gravity and the large-scale structure of the universe, planets, stars, galaxies. Quantum mechanics, conversely, perfectly describes the world of extremely small scales, the realm of atoms and elementary particles. But these two theories speak different languages and are based on fundamentally different principles. Until we can unify them into a single theory of quantum gravity, we cannot accurately describe what happens in extreme conditions, such as the center of a black hole or the moment of the Big Bang, or, in our case, the moment of the Big Bounce. It is precisely at this point, where the entire universe is compressed down to Planck scales, that both gravitational and quantum effects become equally important. What happens to spacetime under these conditions? Does it break down into discrete quanta? How does matter behave? The answers to these questions, which a future theory of quantum gravity must provide, are what will determine whether the bounce is actually possible. One of the leading candidates for such a theory is loop quantum gravity, or LQG. Unlike string theory, it does not require additional dimensions. Instead, it posits that spacetime itself is not smooth and continuous, but rather composed of tiny, discrete loops or nodes. According to LQG, there is an absolute upper limit to the density of matter. The universe cannot be compressed into an infinitely dense point. When density reaches this ultimate limit, gravity flips from being an attractive force to a repulsive one, and it is this inherent quantum repulsion that triggers the Big Bounce. Thus, loop quantum gravity naturally predicts a cyclic nature for the universe, replacing the classical singularity with a quantum bounce. If this theory holds true, then the cycles of expansion and contraction are not merely a hypothesis, but a fundamental property woven into the very fabric of reality. This means our universe must have originated from a previous one, and it cannot fail to generate the next. It is an eternal and inevitable process, hardwired into the very foundations of existence. Let's take a moment to imagine we live not just in a cyclical universe, but in one that repeats exactly. Every single cycle is identical to the last, down to the final quantum. What does this imply for the concept of free will? If your every action, every thought and every feeling was predetermined in the preceding cycle and will be reproduced exactly in the next, do you even have a choice? This question immediately brings us back to the ancient debate between determinism and free will. Determinism is the philosophical stance holding that all events, including human actions, are wholly determined by previous causes. Under classical Newtonian physics, the universe was envisioned as a giant clockwork mechanism. Theoretically, by knowing the initial position and velocity of every particle, one could predict the entire future and reconstruct the entire past. In a universe like that, free will is merely an illusion. With the advent of quantum mechanics, with its uncertainty principle and probabilistic nature, it seemed that a space for free will had finally opened up. On a fundamental level, the world appeared unpredictable. However, the idea of eternal recurrence, in its strictest form, slams the door shut, returning us to an even harder form of determinism, superdeterminism. Your life isn't just predetermined by the laws of physics and initial conditions, it is predetermined by the fact that it has already happened an infinite number of times. You cannot make a different choice because in the previous cycle you did not. This might seem like a deeply depressing prospect, one that strips life of all meaning. Why bother trying? Why strive for good if everything is already sealed? But there is another way to look at this. Just as in Nietzsche's thought experiment, this knowledge could imbue your actions with unprecedented significance. If your action will be repeated eternally, you must execute it in such a way that you are willing to relive it again and again. This forces us to approach every moment of life with utmost seriousness and responsibility. Every choice becomes an eternal choice. Perhaps free will lies not in the ability to change the sequence of events, but in the capacity to accept your destiny and live it out with dignity, courage, and love. This is not freedom from fate, but freedom within fate. It is the ability to say yes to the eternal recurrence, transforming it from a curse into a blessing. Our journey through the cycles of time wouldn't be complete without mentioning another type of cyclical process predicted by some cosmological models, the concept known as eternal inflation. As a reminder, cosmic inflation is a hypothetical period of ultra-rapid expansion that occurred in the very first moments after the Big Bang. The theory of eternal inflation suggests that once this process begins, it never fully stops. The universe as a whole, or perhaps the multiverse, is perpetually expanding. However, in certain regions, inflation randomly halts. In these areas, bubble universes like our own are born. Inside such a bubble, inflation stops and the usual, slower Big Bang process begins. But outside that bubble, space continues to inflate at a staggering speed, constantly spawning new bubble universes. This process is infinite. It generates an endless supply of universes, each potentially operating under its own distinct set of physical laws. In such an infinite multiverse, everything that can happen must happen, and it will happen an infinite number of times. This leads us to yet another form of eternal return. Somewhere out there, in the boundless expanse of the multiverse, another bubble exists where history unfolded exactly as it did in ours. It contains an exact replica of our galaxy, our planet, and of you. And there are infinitely many such copies. This isn't a temporal cycle, like the Big Bounce or Penrose models suggest, but a spatial one. Your life isn't repeating through time within the same universe. It's repeating across space in an infinite number of parallel universes. From a philosophical perspective, the result is largely the same. Your life is not unique. It is simply one of an infinite number of identical instances. This forces us to ponder the very nature of selfhood and identity. What makes you, you? If there is an infinite number of your exact copies living the exact same life, where exactly does your self reside? Is it a unique property of this specific combination of atoms, or is it an abstract pattern realized across multiple locations? These questions push far beyond the boundaries of physics, yet they inevitably arise when we attempt to grasp the boldest and most expansive theories about the fundamental structure of reality. Let's explore another fascinating concept related to cyclic time, one that draws heavily from the fields of computer science and theoretical physics. This is the computable universe hypothesis, also known as digital physics. At its core is the assumption that the universe, at its most fundamental level, is not just a collection of particles and fields, but rather a gigantic computer running a specific program. Every process, every particle interaction is simply an elementary computational operation. The entire evolution of the universe is therefore the output of this cosmic computer. If this is true, it raises a critical question about the nature of this program. Is it infinite, or does it have a finite length and eventually begin to repeat itself? Imagine a simple computer program designed to generate pseudo-random numbers. While these numbers appear random, they are actually produced by a deterministic algorithm. If that program runs long enough, it will inevitably start repeating the exact same sequence of numbers. In other words, its behavior is cyclical. If our universe is indeed such a computer and its program, meaning the laws of physics, has a finite complexity, then its history must eventually begin to repeat itself as well. The state of the entire universe at any given moment can be described by a finite number of information bits. The total count of all possible states, although astronomically vast, is ultimately finite. If this is the case, sooner or later the universe must return to a state it has previously occupied. And because its evolution is fully deterministic, from that point forward, its subsequent history will precisely repeat the previous cycle. This is known as the Poincaré recurrence theorem, applied here to the entire cosmos. It states that any closed system with a finite number of possible states will eventually return to a state arbitrarily close to its initial configuration. In this worldview, cyclicity isn't the result of exotic cosmology involving bounces or branes. Rather, it is the inevitable mathematical consequence of the finite information required to describe our world. We are living inside a gigantic loop because the program running our reality is not infinite, and every tick of the universal processor brings us closer to the moment when all of history will begin its next iteration. When we look at various cyclic universe models, the immediate question is, do we have any observational data that can back up or disprove these bold ideas, or will they forever remain purely speculative? As we've mentioned, one of the most promising avenues is searching the cosmic microwave background, CMB, for relics of previous cycles. This could involve the Hawking points predicted by Penrose, or other anomalies that simply don't align with the standard inflationary framework. For instance, certain big bounce models predict a specific spectrum of gravitational waves, waves that would have been generated during the contraction and rebound phase. If future observatories can detect and measure these primordial gravitational waves, we could, in theory, finally differentiate the bounce scenario from the inflation scenario. Another path involves precisely measuring the properties of dark energy. We need to determine if it is a true cosmological constant, or if its density changes over time, as hypothesized by quintessence models. If future observations reveal that dark energy is weakening or might even reverse its sign, that would be powerful evidence supporting the possibility of a future Big Crunch. Scientists are also searching for possible deviations from general relativity under conditions of extreme gravity. If a loop quantum gravity is correct, its effects could manifest, for example, in how matter behaves near black holes, or in the specific characteristics of gravitational waves produced by mergers. Naturally, all these searches are at the absolute cutting edge of technology and theoretical physics. The signals we are seeking are incredibly faint, making them extremely difficult to isolate from background noise. For now, the standard inflationary Big Bang model still aligns best with the existing data. It's simpler and doesn't require the introduction of such exotic physics, but science never rests. Perhaps in the coming decades, new, more sensitive telescopes and gravitational wave detectors will provide the crucial answer to this fundamental question. We might finally be able to see not just a snapshot of our infinite universe, but the faint shadows of the one that existed before. Let's circle back to our human experience and see how the idea of cyclical time is reflected in our perception and psychology. We've already mentioned déjà vu, but there are other, far deeper resonances. The concept of karma, central to many Eastern religions, is fundamentally an idea of cycles. Our actions in this life determine the conditions of our next birth. This is the endless chain of cause and effect, samsara, from which liberation can only be achieved through enlightenment. While this isn't a physical theory, it embeds the same concept of repetition and consequences that stretch far beyond a single lifetime. On a psychological level, we often live out our own internal cycles. We repeat the same behavioral patterns, make the same mistakes in relationships, and constantly regress to old habits. Psychotherapy, in many ways, is the process of recognizing and breaking these unconscious loops. Perhaps this personal inclination toward repetition is merely a reflection of a more fundamental cosmological principle. Even in our creativity, in the stories we tell, we constantly revert to cyclical structures. The concept of the monomyth, or the hero's journey, described by Joseph Campbell, is inherently cyclical. The hero leaves their ordinary world, undergoes trials in the supernatural realm, obtains a reward or knowledge, and returns to revitalize their home world. This structure underpins countless myths, fairy tales, and modern films. It resonates with us because it mirrors our own experience of growth and transformation, which is equally cyclical. We are constantly moving through cycles of crisis and renewal. The idea of a cyclical universe is appealing to us not just because it's scientifically elegant, but because it profoundly aligns with our inner experience. It tells us that the end is not always the absolute conclusion, that destruction can be generative, and that we always have a chance for a fresh start, for a new turn of the spiral, to become a little better in the next cycle, whether that cycle is personal or cosmic. When we discuss the cyclic universe theory, we mostly focus on two primary futures, either perpetual expansion or a collapse followed by a big bounce. However, there is a third, intermediary, and highly specific possibility that directly relates to what we call the universe's geometry. According to general relativity, space-time can possess one of three distinct geometries. It can be flat, resembling a sheet of paper. It might be open, with negative curvature, like the surface of a saddle. Or it could be closed, defined by a positive curvature, much like the surface of a sphere. In the first two scenarios, flat or open, the universe will expand forever, assuming dark energy remains present. But in the third case, the closed universe, its fate is already sealed. A closed universe has a finite volume, yet remains boundless, much like the Earth's surface. You can walk on it endlessly without ever hitting an edge. Regardless of dark energy, such a universe is ultimately destined to collapse. Gravity will inevitably overcome all other forces. This is the only scenario where the Big Crunch is absolutely guaranteed. Currently, our observations indicate that the universe is flat with extremely high precision. Its curvature, if it exists at all, is vanishingly close to zero. This provides strong support for the theory of inflation, which specifically predicts this kind of flatness. However, our measurements are not perfect. It remains possible that the universe possesses a very subtle positive curvature that we simply cannot detect yet. If that were true, we would be living on the surface of a gigantic, four-dimensional hypersphere. While it is expanding now, in the distant future, it would reach a maximum size and eventually begin to contract. This specific scenario makes the idea of a big bounce the most natural and inevitable outcome. If the universe is indeed closed, then cycles of expansion and contraction might be an intrinsic, inherent property of existence itself. It's like breathing, an inhale, expansion, and an exhale, contraction, forming two phases of a single, continuous process. In such a universe, the problem of escaping into infinity vanishes. Everything contained within it will eventually return, ready to participate in the next cycle. The question of the universe's true geometry remains one of the core unsolved issues in modern cosmology. Future, even more precise measurements may provide a definitive answer, potentially settling the ultimate fate of our world and confirming its eternal, cyclical nature. We've spent a lot of time discussing how one universe succeeds another. But what exactly is carried over from one cycle to the next? Are we talking only about the fundamental laws of physics, or is there something else at play? Let's examine this question through the lens of complexity. Our universe is becoming increasingly complex over time. Beginning as a simple, homogeneous soup of particles, it has evolved into incredibly intricate structures: galaxies, stars, planets, and ultimately, life and consciousness. This process of escalating complexity might seem, at first glance, to violate the second law of thermodynamics, which dictates the constant growth of disorder. But in reality, they are two sides of the same coin. The creation of local order, such as a living organism, is always balanced by an increase in overall disorder or entropy in the surrounding environment. For example, the Sun, acting as a source of low-entropy energy, allows life on Earth to build complex structures. Yet in doing so, the Sun itself and the universe as a whole becomes more chaotic. Now let's consider what happens at the end of a cosmic cycle. In the Big Crunch model, all this accumulated complexity, galaxies, stars, and information, would be annihilated in a fiery crucible. It appears that every cycle starts over from scratch, returning to a simple, homogeneous state. But is that truly the case? Some theorists, such as the aforementioned Lee Smolin, propose that the mechanism of universal rebirth might be imperfect. It might retain certain information, a residue of the complexity from the previous cycle. This is similar to how DNA passes on information about the organism's complexity from one generation to the next. Perhaps there are cosmological genes that are passed through the Big Bounce. In this scenario, the universe could evolve, not just in terms of changing physical laws, but also by accumulating complexity. Each subsequent cycle could potentially be more complex than the last. It might possess a greater potential for the development of life and consciousness. In this thrilling new vision of reality, we are not merely random inhabitants of one of an infinite number of meaningless repetitions. We may be part of a grandiose process of cosmic evolution, a process where the universe learns, develops, and becomes increasingly complex, and perhaps even more intelligent with every new rebirth. Our consciousness may not be the final destination, but simply a stepping stone in this infinite ascent. Let's return to Penrose's theory, because it offers arguably the most radical and elegant perspective on time and its eventual end. The central idea behind his conformal cyclic cosmology, CCC, is that the physics governing the universe becomes scale invariant in two extreme states: the beginning, a hot, dense singularity, and the end, a cold, empty infinity. This is what we call conformal invariance. What does this mean in plain English? Imagine you have a photograph. You can zoom in or zoom out, and yet all the proportions remain the same. The angles stay the same. The shapes remain the same. The universe acts similarly in these two extreme states. Its physical laws don't change whether you stretch or compress it. Penrose argues this happens because in these conditions there is nothing in the universe that possesses rest mass. At the beginning, it's a hot plasma of massless particles. At the end, after all the black holes have evaporated, it's a cold gas of massless photons. And without mass, as we've already discussed, the concepts of time and distance lose their meaning. There are no clocks to measure time and no rulers to measure distance. And this is where Penrose executes his stroke of genius. He reasons, if scale doesn't matter, let's simply squish the infinitely large and empty universe of the future down into an infinitesimally small point. Physically speaking, nothing has changed, but that infinitesimally small point is the singularity of the Big Bang. Thus, the end of one world becomes the beginning of the next. This isn't a physical process of contraction like in the Big Bounce model. It is more of a mathematical identification. The future infinity of one aeon is identified with the initial point of the subsequent aeon. It's analogous to a world map where the eastern edge connects perfectly with the western edge. You can sail endlessly eastward and eventually arrive at that same point from the west. Similarly, by moving infinitely into the future, you loop back into the past. Time in this model is genuinely a closed circle, and most strikingly, this model solves the problem of entropy. The immense entropy generated in our world, according to Penrose, is carried over into the next aeon, becoming the ordered foundation for its beginning. This is one of the most beautiful and audacious ideas in modern science, forcing us to view the nature of time, space, and eternity in an entirely new light. Let's consider another question, one that inevitably arises when we contemplate a cyclical universe. If these cycles truly exist, are they identical, or is there room for randomness and novelty in each iteration? This is where we once again face the conflict between classical and quantum physics. If our universe were purely a classical, deterministic machine, and if, at the end of a cycle, it returned to the exact same initial state, then yes, its subsequent history would be an absolute carbon copy of the previous one. It would be Groundhog Day on a cosmic scale. Every particle would retrace its path, every star would ignite and expire at the exact same moment, every living creature would live the identical life. However, we know that at a fundamental level, our world is governed by the laws of quantum mechanics, and quantum mechanics is inherently probabilistic. We cannot precisely predict the exact moment a specific radioactive atom will decay. We can only speak to the probability of that event. Similarly, many processes in the universe, from the formation of galaxies to mutations in DNA, are fundamentally rooted in quantum randomness. What does this mean for cyclic models? It means that even if the universe begins a new cycle with the same macroscopic parameters, the same density, temperature, and fundamental laws of physics, its microscopic history can be drastically different. The quantum fluctuations in the early universe, which later grew into clusters of galaxies, would vary with every cycle. Think of it like rolling dice. Even if you roll them from the same position with the same force, the result will differ slightly each time because of microscopic fluctuations. Thus, every new cosmic cycle is essentially a fresh roll of the dice. In this new iteration, Galaxies might form in different locations. Stars could have varying masses. On planets like Earth, evolution might follow a completely different trajectory. Perhaps in one cycle the dinosaurs never go extinct. In another, intelligent life could arise on Mars. In a third, there might be no life at all. This implies that eternal recurrence is not a slavish repetition, but rather an act of eternal creation. The universe plays a new game every time, using the same rulebook but yielding a unique result. And in this infinite sequence of variations on a theme, every possible history is eventually realized. Our own life, in that case, is unique to this specific cycle, but it is also just one iteration in an endless tapestry of versions that have been, are, and will be. The universe we inhabit seems almost impossibly welcoming, perfectly suited for life. This observation forms the core of the weak anthropic principle, which essentially states we observe the universe the way it is because, if it were significantly different, there would be no observers, like us, here to witness it. Consider gravity, for example. If it were even slightly stronger, stars would consume their fuel too rapidly for life to evolve. If it were slightly weaker, stars and planets wouldn't have formed at all. This assertion sounds almost like a tautology, a statement true by definition, but it gains profound depth when viewed through the lens of the multiverse or cyclic cosmology. If an immense, perhaps infinite, number of universes or cycles exist, each featuring its own unique set of physical laws and initial conditions, then it's hardly surprising that we find ourselves in one perfectly suitable for existence. It's akin to waking up in a house where the temperature, humidity, and air composition are absolutely perfect for you. If this were the only house in existence, that would be a genuine miracle. But if it's one of a trillion houses, each with varied settings, it's inevitable that you would be found in a habitable one. You simply couldn't wake up in the one with a poisonous atmosphere. Similarly, we, as observers, can only exist, by definition, in a welcoming universe. Cyclic cosmology provides a superb framework for the anthropic principle to operate within. In a model where each cosmic cycle is born with a random assortment of fundamental constants, the vast majority of cycles would be dead, starless, lifeless voids. But sooner or later, this cosmic lottery guarantees a winning ticket, a configuration of constants precisely like ours. And it is exclusively within these successful cycles that intelligent beings will emerge, marveling at how perfectly tuned their world appears to be. Thus, the cyclic model offers an explanation for the universe's fine-tuning without appealing to the idea of divine design or astronomical luck. Our universe is so well suited for us not because it was engineered specifically for our benefit, but because we could only possibly arise within such a setup. And these habitable universes, in turn, are merely one outcome among the infinite possibilities generated by the eternal cycle of cosmic birth and death. We've mentioned black holes several times as key players in the universe's ultimate fate, especially within Roger Penrose's theory. Let's take a closer look at their specific role. Black holes are, in a sense, the ultimate endpoint of matter evolution in our current eon. They are the most highly entropic objects in the cosmos. All the information and structure of the matter that falls into them is irrevocably lost, converting instead into pure entropy, tied directly to the area of their event horizon. In the scenario of eternal expansion, long after all the stars have burned out and all ordinary matter has decayed, supermassive black holes will remain as the last macroscopic objects in existence. They will then proceed to evaporate excruciatingly slowly over trillions upon trillions of years, returning their mass energy back into the cosmos as Hawking radiation. Thus, black holes act as the universe's ultimate recyclers. They take ordered matter, stars, gas, and planets, and transform it into the most disordered state possible, thermal radiation. From Penrose's perspective, this exact process is what prepares the universe for its transition into the next eon. Black holes destroy all mass, leaving behind only massless photons, a requirement for establishing conformal invariance and allowing the universe to reboot. In Lee Smolin's model of cosmological natural selection, black holes play an even more active role. They are not merely recyclers, they are the seeds of new universes. In this theory, every collapse of a star into a black hole simultaneously gives birth to a new Big Bang, a new universe, somewhere else. In this worldview, our universe is literally teeming with the embryos of future cosmoses. These mysterious and terrifying objects might not represent the end of everything, but rather the crucial link in an eternal cycle of cosmic regeneration. They may serve both as a womb nurturing new worlds and as a cleansing fire preparing the old one for rebirth. Understanding the true nature of black holes and the processes occurring within them is therefore the key to grasping the ultimate fate of our universe and perhaps even its origin. As we conclude our scientific exploration, let's pivot to its deeply human existential core. How do we live with the awareness that we might be part of an infinite, repeating cycle? This single idea can provoke drastically opposed reactions depending on our individual worldview. For some, it is a source of profound despair. If everything repeats, then true progress is impossible. History ceases to be an ascent towards some ultimate goal and becomes nothing more than a pointless, relentless treadmill. All our achievements, all the art, all the scientific breakthroughs will be obliterated at the end of the cycle, only to be recreated in the next. This robs human endeavor of any ultimate meaning. We become Sisyphus, eternally rolling the boulder up the mountain, knowing it is destined to roll back down. In this vision, there is no final victory of good over evil, no salvation, no paradise. There is only the eternal recurrence of the same. But for others, this very same idea can be a source of immense solace and liberation. If the universe is truly eternal and self-sustaining, it doesn't need an external creator or a final destination to possess meaning. Its meaning resides simply within its own existence, within this endless dance of creation and destruction. It is not moving towards anything, it simply is. And we, as a part of it, can find meaning not in achieving some external objective, but in the fullness of experiencing every single moment. The concept of cyclicity lifts the crushing weight of responsibility for the final outcome of history. Our task isn't to save the world once and for all. Instead, it is to live our lives, to play our role in this specific act of the cosmic drama with maximum completeness, mindfulness, and love. Furthermore, the idea of eternal regeneration gives us a profound sense of rootedness and belonging. We are not just accidental specks of dust flung into a hostile and indifferent cosmos that will vanish without a trace. We are an integral part of an eternal, indestructible process. We have always been, and we always will be, in one form or another. Our very atoms participated in countless previous cycles and will take part in countless future ones. This thought can offer a feeling of deep peace and acceptance, much like the quiet serenity we find when watching the ceaseless movement of ocean waves or the reliable turning of the seasons. To wrap up our extensive discussion, let's once again cast our gaze across the landscape of ideas we have explored. We began with a deceptively simple, yet profoundly disruptive question. What if time is cyclical? We discovered that this notion, ancient as civilization itself, finds powerful resonance even in the most cutting-edge modern science. We explored the theory of the Big Bounce, where our universe is born from the ashes of a previous one, compressed to its absolute limit. We saw how this model must contend with two formidable adversaries, dark energy, which attempts to rip the cosmos apart, and entropy, which threatens to render each succeeding cycle increasingly chaotic and devoid of life. We then delved into the astonishing framework of Roger Penrose's Conformal Cyclic Cosmology, or CCC, where the infinitely distant and empty future of one eon magically transitions into the infinitely small and hot beginning of the next. In this worldview, there is no need for collapse or rebound. Instead, we find only a smooth, mathematically elegant transition that effectively erases the boundary between the end and the beginning. We also glimpsed the even stranger world of string theory, where our universe is merely a brane, or membrane, floating in higher dimensions, and its birth is the result of a collision with another such brane. This eternal cosmic dance of branes in hyperspace similarly generates an endless chain of universal births and deaths. We recognize that all these theories, however disparate they may seem, are united by a common objective: to bypass the problem of the initial singularity, that uncomfortable question, what came before the beginning? They replace the notion of a single, one-off creation event with the concept of perpetual process and eternal self-renewal. They propose that the universe requires no absolute beginning because, in a fundamental sense, it never truly started and will never truly end. It simply exists, engaged in an eternal cycle of transformations. We currently lack a definitive answer as to which of these theories holds true, or indeed, if any single one of them is fully correct. We stand on the boundary of our knowledge at the point where science converges with philosophy and borders on poetry. Yet the mere existence of these ideas expands our consciousness, forcing us to redefine the most fundamental concepts: time, existence, and our own place in this magnificent, incomprehensible, and potentially eternally recurring cosmic drama. Our long journey through the cycles of time is drawing to a close. We started with the intuitive concept of time as a straight river and arrived at the dizzying realization of a boundless cosmic ocean where waves of births and deaths endlessly succeed one another. We've seen that modern science, in its most audacious forms, is circling back to ancient, mythological images of cycles and rebirth, yet filling them with new mathematical and physical substance. We have come to understand that the familiar picture of the Big Bang might conceal something far more monumental: an infinite succession of universes. Perhaps our universe bounces off itself in the Big Bounce model, evading singularity thanks to the laws of quantum gravity. Or perhaps it is merely one eon in Penrose's infinite chain, where the slow death of cold and void paradoxically gives way to the fiery birth of a new world. Or maybe our entire reality is simply the result of invisible membranes colliding in a multidimensional space. Each of these theories, in its own way, resolves the central mysteries of cosmology: the problem of the beginning, the problem of homogeneity and flatness, and the problem of fine-tuning. And each one unveils a new, fascinating perspective, a perspective of a world that was neither created nor will it ever be destroyed. A world that is self-sufficient, eternal, and perhaps ever-evolving. We also touched upon the philosophical implications of these concepts. The idea of eternal recurrence compels us to rethink the notions of meaning, free will, and the uniqueness of our lives. It can both terrify us with its fatalism and inspire us to live every moment to its fullest, as if it were destined for eternal repetition. This knowledge doesn't provide ready answers, but it asks the right questions. It shifts our focus from the mundane concerns of daily life to the eternal, fundamental mysteries of existence. And perhaps this is the main purpose of science, not just to explain the world, but to awaken in us a profound sense of wonder and awe towards it. May these thoughts remain with you as you drift off to sleep. Sleep, which is itself a small cycle of death and rebirth, the end of one day and the beginning of another. Perhaps through these daily cycles, we are unconsciously rehearsing the great cosmic rhythm of which we are all a part. We have covered a vast distance, haven't we? From a simple question about the nature of time, we reached the very boundaries of modern physics and philosophy. We have seen that the universe might not be a single, disposable story with a defined beginning and end, but rather an eternal poem where the verses repeat, perhaps with slight variations, or perhaps even exactly as they were before. Theories like the Big Bounce, Conformal Cyclic Cosmology, and colliding branes, they all point toward the same profound possibility, that our world is just one link in an infinite chain. Perhaps the most critical takeaway is that these ideas are no longer just pure speculation. Scientists are actively searching for confirmation in the cosmic microwave background, in gravitational waves, and in the properties of dark energy. It's possible that we will get the first hints of the answer within our lifetime. And whatever the ultimate truth may be, the mere possibility changes everything. It tells us that nothing truly vanishes without a trace, that an ending may simply be a new beginning. that the very fabric of reality could be cyclic. Thank you for spending this time with me, pondering these truly profound questions. I hope this journey has been as fascinating for you as it was for me, and that it helps you drift off to sleep peacefully. If you enjoyed this lecture, please give us a like and subscribe to the channel so you don't miss our next explorations into the worlds of science and the cosmos. And now, before you completely surrender to sleep, I want to leave you with a final thought. Write your answer in the comments when you wake up. If you knew for a fact that your life, with all its joys and sorrows, would repeat in the minutest detail an endless number of times, what is the one thing you would change in it right now? Good night and sweet dreams of eternity.